acceptable. I definitely had one for you. Whatever. Yeah. Thanks. That was easy. Let's get started. Lord, thank you for bringing us together this afternoon. Thank you for everything that you do for us and all the blessings that you've given us. I pray that you would just continue to help us throughout the semester, that you would give us what we need, even if we don't recognize it at the time. Pray that you would help everybody to just focus on their tasks at hand and accomplish the things that they set out to do. In your name we pray. Amen. All right. What are we doing today? We are going to recap what we did last. Then we're going to talk about how to do trigonometry for 2 links instead of 1 link, which is super fun. It's like you get to do twice as much trigonometry in a single problem, which can't be bad, right? It's like 50% more trigonometry. And then you're gonna do some problems, or specifically one problem. You've got a problem. That's just one problem. But you guys will do a problem. Double arm thingy. Yep, sure. Double is that means there's 2 of them. We're gonna talk about this, right? But yeah, so how do we end up doing a two link problem, right? And it doesn't just extend to robotic applications, right? There are plenty of mechanisms that have 2 or even 3, what we call 3 links, right? Linkage mechanisms. And this is typically how you would figure out the angle of all of them, right? And where they need to be. And the more links that you add, the more, say, variability you add to your system. What do I mean by that, right? The more links that you add, the more methods or the more configurations you have to reach a specific endpoint, right? And so things get trickier as we do more and more, but we're going to focus at most. We're going to talk more about it today, so I'm going to hold off on full explanation of the double arm thingy, which from now on, next year, I will actually put that as the title of the slide. This is the double arm thingy. So it's no, but you could clear the response of that. All right, so to recap, right? Where is the end effect? There's supposed to be like a point here, right? Maybe. Did it not copy the graph? There we go. All right, for a 1 link robot, right? We have 1 link and I want to find the endpoint, right? How do I do this? What information do I have to assume that I have, right? Well, we're going to say that we have, remember, some theta. And if we're asked to find the endpoint, we will also know the length. And if you know the length and the angle, where is the endpoint? So how would I find the X endpoint for link 1? Y1. For those of you who had lab yesterday, right, you should be able to fire this one off really quick. Cosine of theta. X1 is equal to L1 times the cosine of theta. We'll call this theta 1 because it's the first link, right? So what's the Y component then? Yep. Nailed it. Sine theta 1, right? Okay, so that one's not too bad, right? That's just a right triangle, and everybody feels pretty comfortable with that trig, hopefully. And if not, that's fine, because when we start talking about vectors over the next couple of weeks, you're gonna get plenty of chances to practice it. So we'll, by the end of the next, end of the next topic, right, we should be pretty confident with our trig. So what's the next thing that we have to do here? Is this link, okay? Man, so how do I find the end effector of this link, right? Well, this is tricky. Why is this tricky? Because it's really drawn super great here, right? Because we're still measuring everything from this point. And I want to know what this point is in space, right? Well, kind of. What do we know, right? This has some angle here that we're going to call theta 1, right? So what is that? Well, let me go back for a second and see if we can right? So when we look at this thing as a whole, right? The first link, right, makes a line, and we know that that line is at theta 1. And so if we draw an imaginary line extending that all the way in space, right, then still have something that is at theta 1, right? So from the x-axis, we know that that angle is theta 1, and the angle that we're interested in finding now, right, is theta 1 plus theta 2. Okay. And if we know L2, let's try that again so that people can read the handwriting. If we know L2 and we know theta 1 and theta 2, then how do we find x2 and y2? Carver, you have a question? Correct. Correct. So, yeah, it's so the sticking point for a lot of these problems is going to be wrapping our heads around how to reconcile some of these angles, right? There's some geometry that we're going to have to do to figure out what actual angle. But if you can always bring it back to a right triangle and try to figure out what the angle is for that based on what you know, it'll be helpful. Okay. And we'll do a couple examples later where we'll talk about this more as well. Right. So for the second link, if you know theta 1 and theta 2, right, I think it's pretty clear that based on what we had above, right, this would just be the total angle, right? Theta 1 plus theta 2. Yeah. Is everybody cool with that? Right? Because this total angle, if you wanted to call this, let's call that beta, right? Just because throw Greek letters around like it's nobody's business, right? It's a cool looking one. Not as cool as Zeta though, right? But you know, that's you guys know why Zeta is shaped like that? Because Zeus is the god of lightning and it looks like a lightning bolt. Made that up right now. All right. It should be L2. Thank you. Thank you. Thank you. Catch. So L2, like I said, L2 times cosine of theta 1 plus theta 2. And so X or Y2 would be, you know, L2 sine theta 1 plus, or there it is, plus theta 2. All right. And so how do we find the total? Well, I'm going to try my best to draw this unencumbered. All right. I'm going to erase all this stuff, right? So I want to get the total from the origin out to, right? So I want to find this point, right? I want to know what is that line, right? Well, I don't need to know that line. I want to know how to get to that point. Okay. All right. So for those of you who were like, this is a preview of vectors, which we will start next class, or cap of lab from yesterday. That's the resultant. That's the resultant position from measured from the origin out to P. That's the resultant vector, right? And we're adding these two vectors up together. And so if we have this, we can say that, and finally, I'm gonna, so I promise there's a point to this, right? So look, there's a triangle, right? There's a big red there in red, right? We are very comfortable with red triangles. Everybody loves red triangles. They're the best, right? Don't tell the other triangles, right? But they're your favorite kid, okay? Everybody's got one. It's fine. You're probably the favorite kid, or at least you think you are, right? And that's how it works. Everybody thinks that. But check this out. If I take the y component here, if I drew it well, which I didn't, all right, it would have, right? So make it look good. So had I drawn an actual straight line, what we would have seen is that by adding the y components, you have the same length as the red line. And by adding the x components of these two triangles together, check this out. That one actually I drew well, right? You have the length of that, right? So we can decompose both of these triangles into right? So if you added x1 and x2, you would get the total x position of that point. And if you added y1 and y2, you would get the total y position of that point, right? So there we have it. Like I've been alluding, this is going to come back in vectors in some way, right? So these things are done. We have homework 3 due on Friday before class on paper. Homework 4 due the following week, also on Friday in class before. Yeah, Mark. I am almost done. They'll be graded by next class. And I will post solutions tonight. Okay. Then I'm still trying to figure out how I'm going to hand it back. So make sure your name tags are folded, because I'm going to put your homework inside of your name tag for next class. So you just pick it up that way. Okay. And then we've got our first quiz on the 7th. First quiz on the 7th. All right. Don't worry about what happens after that on the next class after the 7th. Okay. Don't worry about that. All right. So now I told you guys in the last class we were going to start and you guys are going to get a problem. So we're going to do a time trials. Okay. I'm going to give you an amount of time. Get with your groups, right? You can use notes in MATLAB or a calculator. You cannot use any sources out of those things, right? Here's the problem. You are find the end position of a link, a 2-link robot. The link 1 is 2 feet, link 2 is 1 foot, theta 1 is 200 degrees, and theta 2 is. Now, I also have a present for you before you start all of this. If you're interested in drawing this to scale, I have protractors that everybody can use. Ooh, fancy. I had to empty multiple bank accounts for these protractors, right? My kids can't go to college now, but you guys have protractors, which is fine. Also, they're not yours to keep. I'm just going to say that these are communal for everybody who's taking the class over the course of the semester. Okay. I hope there's enough. Some of them might have gotten legs. You can take one and pass it down. Take one and pass them around. Take one and pass them around. And I don't think we're going to have enough for everybody. So try to share one per group if that's possible. All right. My timer there, which is problematic, because I was going to give you guys 15 minutes. There it is. All right. You guys can start now. Maybe. Just start. You got 15 minutes. I'll be around. So on the bottom, you have a team number. So find which one were you in? It's going to be towards the back. Is right, probably right around where you're sitting. Sorry.
I feel like
What?
that's a right angle. Can we just solve hypotenuse for that and it'd be like √5? Or
No,
why couldn't you, since you have the right angle for that?
because you don't know. So first of all, it's -90, right?
Turn that way.
It's going to go down. So it's going to go down, and that's √5. Trying to think of what √5 is off the. So you could, but it's not in the right coordinate axis, right? Because it's not, because the X isn't aligned along the X axis. It's aligned here. You're not going to be in the right coordinate reference range. Yeah. What you guys got? What you guys got? Let me see. Okay, so y is minus 1. Let's see. So you don't have that drawn in the right way, right? So remember, theta 1 is going to be all the way around, and so theta 2 is going to be off of theta 1, right?
Yeah.
So I think the issue, right? So make sure that you're using the right angles inside of your. It's not right. Should be minus 1 point. Yeah, that guy and that guy. Sorry. I realized I didn't send it. I'm sorry. Yep. Yeah. All right, what you got?
Think of it as an order.
No. No. No.
We're not 4K.
Draw it first and then see where it tells. Jose, I can't get past this. Sorry. Let's switch over.
Does that look right?
No.
So would this not be one?
So this is supposed to be, is this 90 or negative 90? Isn't negative 90, 90 degrees off of this line? It'll be down here, not up there. But negative 90 would also be 270 degrees, which would be down.
Straight down?
Yeah.
Okay.
So you just have it flip. Yeah. Yeah. Oh, you guys are close. So show me about your X. Let me see your X here. What's going on?
X, well, it'd be like, 2, because like this 2 cosine, gets you point right here with the side.
And so. So this 90 doesn't go straight down like that. Off 90 degrees off of this line. That way. So that's where you're having some okay. Okay. So you guys do this. This is your theta. Where's theta 1 at?
Theta 1, but then it connects.
So
to
theta.
7.
So theta 1 is supposed to be the first length here, right?
Yeah.
At 200 degrees, and then off of this
And then
one,
off that is the negative 90.
right? Negative 90 from this line. So this way right here,
So it just comes straight down, right?
not straight down, straight down. So it makes 90 degrees with this line.
Oh, with
Yes. Yes. What's up?
The final answer is that one.
Okay. Yeah, draw it out and see where the endpoint is, and then that'll help with understanding where your coordinates are supposed to be. Yeah. So measured,
Flat or measured?
it's measured from the other link.
Okay, so it's 90 degrees from the downward.
Yes.
All right. Thank you.
Yes, 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 yes. One second. All right, excuse me. Okay. So, Ronald. Yep. Nailed it. Yeah. So chocolatiers, that's right. Nice. Mhm. Oh, sorry. All right. What's up? Wait, did you? wait, What's are you reconsidering now?
This was, all right.
That's correct.
Yeah, that's right. So our first.
Maybe you should. Jack is up. All right. $90 off of this line. So if this is an
Yeah.
imaginary line all the way out,
Oh, that's how I drew it right here, 90 degrees
yes, like that. Yes. What's the answer? What'd you get as P? No, you just.
No?
Yeah, double check your calcs. Here, what you got?
I want to see if I got this right.
So no, that's not right, but you have a good idea here. It's just that this is not. This is not, right? So. Right, so you got your 200, that's fine. That'll be 20. This is 90 off of here. Perfect, right? So where's your math? What do you got for your math here? This is 2 feet and this is 1 foot, right? So in this case, is it theta? You got to make sure it's theta 1 plus theta 2. That's not always true thing. It's sometimes you have to make sure that you're looking at the right angle. Look at this here. What angle are you measuring? You want to measure this angle, which is not theta 1 plus theta 2. Steve. No, what's going on? It's 90 degrees off of this line, not off of it. Back. All right. Get behind you, Devin. I'm sorry. Just crowded. The president of the university that we need a bigger room. The name Mellow Fellows, that's right. All right, 5 more, guys, 5 more minutes. Yeah, that's me. Dr. Mathman. Thank you.
Did I do it better?
That looks good. What's your answer? Yeah, there you go. You had it right before.
What?
That was correct. Yeah. I told you guys, I said you guys were right, and then I walked away. No, I said this is correct, and then I walked away. Yeah. No. Jeez. What's up?
Got the right. Gee, I drew it here originally, safely, and the intro up here, right?
Okay, so this is, they're both wrong. Okay. But remember where you're measuring the 90 degrees from. This is correct in the sense that you have 90 degrees from this line. This is correct in that it's coming downward. Now put these two.
Right, yeah, that should be negative and negative.
Right,
So
you had the right idea to be negative. Somebody else had the. Okay. So no,
really,
because it's not down here, it's gonna shift where this point is. Right, so double check your math, right? Because this point, so I know I rewrote that that's theta 1 plus theta 2. Always theta 1 plus theta 2. If you're using this angle in here, that's not gonna be theta 1 plus theta 2. You gotta figure out what the angle is gonna be. Yeah. Right. So the first one. 3 minutes. How are you doing? All right. Are you? That's crazy. Well, thank you for being here. Appreciate it. So depends on what your drawing looks like, right? So if it looks like this, then yeah, you're gonna have x2, x1 is gonna come out too far, and you're gonna have to subtract x2 from x1 to get the total x, right? Why drawing it's really helpful.
You have just left
Uh,
60 minutes left. And have the fantastic engineering.
Okay.
It's 5.
Okay,
2 minutes.
awesome. Thank you. Here, what's up?
I have, so the 200, that's in the right place.
Right, so yeah.
Right.
So you took 20 times sine for y, or 2 times 20 times of sine, 2 times sine of 20 degrees. There we go. Brain, come on. For y, and 2 times cosine of 20 degrees
So
for
it'd be
x, right?
-20 instead of 200, because I just did.
So you know that this
True
is gonna be a
sine.
negative length, right? So you can do that on your own, or you can use, you can actually put 200 in there and it'll tell you what that is and take care of the quadrant for you. It'll do the same thing.
How do I? Figure out?
And so this, right, that's 90, right? So if this comes out, you know that this is 20 to here. And so now we've got to do right? So the easiest way that I can explain this is that if you draw a 90-degree angle here, right? This angle is now off of the y-axis, right? How much should we turn this by? Turn by 20 degrees. Okay, so
So would this be the 9? No, would this be 90 or would this be?
so if you're doing this, right, think of it this way. Now you've got a new x and y coordinate axis, right? That goes this way. How much should we rotate this from the original? We rotated it by 20 degrees, right? Does that make sense? So another way of thinking about this is, right, this triangle is 20, 90, and 70 here, right?
Right.
So I'll just write 70 there, right? So this by geometry, this also has to be 70 degrees in there. And if you were drawing a triangle all the way out, right, it's going to be 90. This guy is also 70 because now that is 70 and this comes back as 20. So you have to do some hardcore geometry to or you can say that, all right, guys, time's up. Time's up. Time's up. Let's get back to it. Good job. We'll tally up the scores. I'll give you, there's gonna be more. So I realize, right? I realize you're all like, well, this isn't fair because I don't like to work quickly, right? And so there's two types of people, right? There's people who are tortoises and there's people who are hares, right? And our academic system is typically geared towards people who are hares, right? People who can get the correct answer the fastest, right? That's all standardized testing. But you might not be that way. You might like to take your time, and that's fine too. So I've got some activities that aren't going to be time dependent that just let you earn points for working on problems, right? So don't feel like you're never going to get any points. You're going to have opportunities to get points through other means as well, right? You'll see what I'm talking about later, right? Specifically today. All right. Anyway, so there's a couple of things here, right? Let's go ahead and let's talk about this problem, right? Everybody, I thought you guys did great. This is the forward version of this problem, right? We're going to talk about the inverse problem in a minute, right? But this is the forward version. So the first thing we need to do is, you don't need to, but I highly recommend drawing, right? So I'm going to try my best to get some straight lines here, right? Here's my XY axis, right? X and Y. There we go. Okay. And when I did this problem, I definitely used the protractor, right? And got my angles all sorted and everything. And right now I'm just going to do it freehand. So it's going to be perfect. Right? Because there, 20 degrees. Perfect. Right? 200 degrees is just 180 plus 20. So this angle in here is 20 degrees, right? You can call it what you want. We'll call this theta 1. Understanding that, and I think everybody would agree that understanding that that's 20 degrees is pretty tricky. All right, now we've got this other link, and this is where people tripped up. It's 90 degrees, but where is theta 2 measured from? It's measured from the first link, right? And it's negative 90 degrees. So this one's got to be down here somewhere. Now that looks like 90 degrees, but I did my best, right? Did my best. So that's the point P that we are after, right down here. P. All right. And so we know that this is negative 90 degrees right there. All right. So what do we need, right? Well, if we're looking at this, the easy thing to do is get X1 and Y1, right? And if you're drawing this while we're doing this, right, this is going to inform us about where our point should be, right? So when we get an answer, we can understand whether or not we're actually in the ballpark, right? And what's going on here. Then if you notice, this comes back, right? This guy comes back. So X2 is coming back and further down, right? And I realize this is not great drawing, and is what it is at this point, right? It's what we're getting. We can also draw a line from here, from here down to there, right? Because we can. It makes a right triangle. Okay. So there's a couple of things that we can do here. Okay. So what's going on? Well, we'll get X1 and Y1 first, right? X1 equals L1 times the cosine of 20 degrees, right? And you can use cosine of 200. If you use cosine of 200, it'll give you the sine appropriately to the quadrant that it is in, right? That will work. Or you can use cosine of 20 and say, I understand that this has to be negative, right? One way or the other. And if you do this, you will get X1 is equal to negative 1.879. Now, do I need to keep that many decimal places? No, you don't. But typically I will hold as many as possible until I'm ready to report my answer. And then I will dumb it down to, 2 decimals and call it a day. Now I realize that goes in the face of everything that the chemistry teachers have taught you because sig figs are king, right? But here we are. All right. Anyway, you can do sig figs in chemistry. That's fine. Sometimes it doesn't make sense in engineering. All right. Y1 is just the sine. 3 degrees. So Y1 is equal to negative 0.6840. All right. So now we've got X1 and Y1. but that's not super helpful, right? Well, I mean, it's helpful, but now we need to find x2 and y2. And I know your compulsion is to look in your notes and say, well, it has to be theta 1 plus theta 2. But that's not always the case. That was the case for the drawing that we had. It's going to change, and we need to be able to figure out what that is. So let me draw this, right? So I'm going to this stuff here just for a second, and we'll talk. The red. So at this point, I'm going to draw another XY axis. Okay. And I realize that might be a little bit confusing, but I'm just redrawing the XY axis there to remind me that everything needs to be in these reported in these X and Y coordinates. And it's going to be helpful because what we are going to see now is that this angle in here has to be 20 degrees, right? Well, is that 20 degrees? Hold on 1 second. Please hold. I'm going to call it phi. That angle is phi. So we've shifted this x-axis by some amount, right? What amount? I already gave away. It's 20 degrees. How do I know that that's 20 degrees? Well, if you look at this right triangle and you look at this right triangle, they make a rectangle with a bisecting line as the hypotenuse, which means that it's got to work out, right? It's geometry. You could also do the much more hardcore geometry, right? And try to figure out all of the angles, right, at the other end, and the Tetris of angles that you can do, right? But this isn't easy. So, all right, I want you to think about this as well, right? We've created a new set of axes here, the purple line and the blue line, right? And they are 90 degrees from each other, right? And to create that, we had to angle one of them at 20 degrees. So doesn't that also mean that the angle from the old y-axis would have to be 20 degrees as well? Right? Are you guys following me, or is this too much geometry? Okay. So what is he talking about? What's this? This guy's crazy. I'm just going to smile and nod. I want him to leave me alone. Okay. Okay. I don't want to do this. I want to do this way. Here's my original XY axes, right? I created a new set of coordinate axes that go like this. Okay, right? And when I say coordinate axes, all I've done is to imagine that this line extends in space for, and this line extends in space forever, right? This is a new X and Y axis. It's just tilted. How much is it tilted by? It's tilted by 20 degrees, right? Because in order to make this, I hold this thing constant and I turn it. How much did I turn it by? 20 degrees. Now the x-axis line, y-axis is in line, right? Turn my coordinate system 20 degrees. This is something that's going to be really common. And when you guys take physics 121, okay, they're going to start doing inclined plane block problems, right? Where you put a block on an inclined plane. You guys do that in physics in high school, right? And so you can do that in the XY axis, right? But it's not like you have to keep track of sines and cosines for everything, or you can tilt your axis to be along the angle of the block, and then you don't have to keep track of sines and cosines. You guys know what I'm talking about? Same idea. You're just rotating your coordinate system. Tilt your head. So another way of doing this is if you're looking at this and you tilt your head 20 degrees and it's drawn correctly, it'll look like regular X and Y. Okay. Called changing your frame of reference. All right. That being said, that is a 20-degree angle. All right. Now, if I overcomplicated that, I apologize. It's not my intention. If you have a better and more simplified way of explaining that, I would love to hear it, because I would love to make that more palatable for everybody, for sure. But I know that that's 20 degrees. And because I know that that's 20 degrees, this is 20 degrees, right? If you want a more graphical representation of that, I can offer you one at a different time, come to office hours. But this is 20 degrees in here. So that means now that our x2 is equal to L2 times the sine of 20 degrees because it's opposite of the angle, right? And x2 is going to be negative 0.420. Oh, nope. Negative 0.3420. So very small. And y2 is just L2 cosine, 20 degrees. And y2 is negative 1.624. Okay. Nope. Sorry, I skipped ahead in my notes. It's negative 0.9397. That's what it is. Man, batting 1,000 right now. Tell you what, feels good. Feels good. All right. So how do we do this? It's just x1 plus x2 and y1 plus y2, right? That's what we're going to do, except that it's not really, it's x1 minus x2, right? Because we went over by some and then we have to come back, right? So x total is equal to x1 minus x2, which as some of you told me is negative 1.537 feet, and y total is y1 plus y2, which is negative 1.624 feet. Okay. That's a lot of stuff, man. Like I said, it's double the fun because you trig more than the one time. You can check this too, right? We can totally check this by plotting where that point is and seeing if two lines that we have the endpoints for line up with it, right? So we can check this. And so let's talk about how to check this. I should probably clear that because that's going to be annoying as it won't clear when I change the slide. All right. So in MATLAB, what did I do? Well, this is an example because we're going to make a two-link robot in MATLAB. Okay. We're going to use the previous two examples and we're going to use stars for the joints. This is not that robot, right? Because it's not the right configuration. All right. When we look at it, the initial position will be in black, final position will be in red. Okay. Yeah, no, I already said those things. Oh my gosh. Okay, so here's a code. Okay. So what are we doing in this code? First thing I'm doing, I'm defining my point pairs. No, I'm going to say we start at the origin. X0 is 0, Y0 is 0. Then I'm going to define the endpoint of the first link, which I'm calling X1. X1 is 1.78. Y1 is negative 0.90. So hang tight for a second, right? And then X2 is 2.758 and negative 1.116. That doesn't track what I just did. But if you go back in your notes to the example we on Friday, that's the starting point of this robot. And then we're going to plot it, right? So I'm going to plot my point pairs. I'm going to plot open square brackets, X0, comma, X1, comma, X2, and my square brackets, comma, open square brackets, Y0, Y2, right? And it'll plot, right? It'll plot X, Y0, Y1 with X1 and X2 with Y2, right? I put my hold on, I put my grid on, and what this is going to do, it is going to plot the starting position of the robotic arm, okay? By the way, if you put parentheses or not parentheses, if you put the percent sign in MATLAB, that's commenting, right? So it doesn't run that code. It knows not to run anything after the percent. Okay. So you can make little notes in your codes, right? And not have to worry about it. All right. And then I'm going to set up this other coordinate, these other coordinate points, X3 and X4 and Y3 and Y4. Those are going to be the starting point and the ending point of my robot arm in the second position, right? So X3 will be for link 1 and X4 will be for link 2, right? So I just needed a different set of variables. And so that's what I did. Notice this tracks with what we just did, right? Our ending position, X4 and Y4 is ending position that we found, right? Okay, so that defines the position of the robot arm at the end. I'm going to set my Y limit to adjust Y axes. Right. I'm going to put a title on there because, you know, I want people to know that this shows the position of robot arms. I want an X label and a Y label so that I can include my units, right? So I know what I'm looking at. And if we do all that, you get something that looks something like this. Okay. Now you're like that's cool. Right? Super cool. Here's 0. And here's 0. That one on the left is the one that we just did. You guys drew that, right? But it confirms what we talked about, right? It is a way for us to check graphically that we got the right endpoint, right? And if you really wanted to, right, you could use the data tip tool to figure out, you know, what the angle is between the x-axis and the final point on the first link, right? To double check that and all those other things, right? There we are. Okay. So let's, all right, first questions. You guys have any questions? I'm gonna throw the code back up for a second. Does have any questions? You all right? Yeah. Man, nothing. I'm killing it. Feel like I'm killing it right now. Yeah, feeling good. You guys are like, what is he talking about? All right, let's talk about two-link robots in the inverse way, right? So we talked about this with single link, right? It's great if you know the length and you know the angle and you want to find the endpoint, but what if I have a specific endpoint and I want to set the robot's angle, right? How do I do that? Well, it's for one arm, right? For one arm, it's not that bad. But how we do that for two arms, right? So we're going to talk about elbow position, right? So the book uses the wrong convention based on what is typically used in practice. Elbow up is θ2 at a negative θ2 and a positive θ2 is elbow down. Okay, so you're like, that's weird, right? I don't understand. And that's fine. So what I want you to remember is this picture. Elbow up means that the elbow is going to be up. Elbow down means that the elbow is going to be down. That's the right way to think about it because it's descriptive of what is happening. If somebody told you it was an elbow up robot and you didn't know anything else, you would assume that the elbow is in this position. No, this is elbow down because your elbow is down. This is elbow up because the elbow is up. Okay. Now, if you think about what the angle means, right? If elbow up is a negative angle, does that make any sense, right? No, right? Well, yes, right? This is elbow down, right? Elbow down I gave you the wrong angle. Let's try that one more time. This is θ2. That's the elbow down position. That's a positive angle, right? This is elbow up. This is θ2 for elbow up. Angle is down. Okay. Does that make sense? So really all you need to know is that if it looks like the elbow is pointing up, that's elbow up. Right? That's what we need. Great. So strategy time. How do I find θ2? Given the right, so I know two side lengths of my right. So I know the lengths, right? Well, how come I have to know the lengths? Well, I mean, you're the one with the robot. You should be able to measure the lengths of the robot arm. Like that's just If you don't know, you can go measure it, right? Like that's the thing. If you're doing this program, if you're doing this problem and you don't have a robot in mind, I don't understand why you're doing this problem, right? You're going to know the length. So if you know the length, right, we know the two sides, we can find length from Pythagoras, right? Good old Pythagoras, right? So that linkage turns into this, right? We can make a right triangle, like I showed you guys earlier. And so we can find the total endpoint, right? We can try that total distance from the origin out to the end, find h squared, right? So why do we want to find h squared? Well, because we have a right triangle that we're dealing with here. When we draw it like this, right? So we can know about where the endpoint is, because we know where the endpoint is, because we have a desired location that we want to go to. We draw a line from origin and make a right triangle out of it to find the hypotenuse or the resultant of that position vector. And then we add back in our lengths. And now we've made non-right. And so law of cosines is our best friend. Okay. Oh, wrong. And so here we go. So we know that this angle is theta. So that means that this angle in the triangle, 80 degrees minus theta 2. Okay. So the length, and we know one angle, law of cosines. Now, notice on this particular one that the 180 somehow magically disappeared here. And I don't know where it went. I didn't make this slide. I'm gonna have to have words with Dr. Jones about it. But so another way of doing this, that you don't have to worry about that 180 minus theta 2. This is how I like to operate with this, right? I'm gonna say that this angle in here, I'm just gonna give it another name. I'm gonna call it beta. What's with the beta? Always with the beta, right? I don't know. This is how I learned it. So I'm gonna call this beta, and guess what? Beta is equal to 180 minus theta 2. And so instead of solving this for that, I solve this for beta, and then I plug it into this equation and solve this for theta 2. So I don't have to worry about, well, did I include the 180? Did I not include the 180? What's the big deal, right? We take the guesswork out of it. Okay. If you would rather do it the other way, make sure you include the 180 in this equation down here. Where would it go? Right? Well, you would have a plus 180 after this, right? Because you brought this over. Well, let's be minus 180 on that side, right? Minus 180. It's the same thing. You just subtract 180. So the real equation, I'll write the real equation down because I know you guys are going to write down this equation. Minus 180. There you go. That's what it is. It's the cosine inverse of that minus 180. Or 180 minus that. Whichever one makes the most sense. Okay. Cool. So that's how we find theta 2. Law of cosines. Right? Law of cosines. Everybody loves law of cosines. Right? So remember, this is a reminder that elbow down means the arm is up. That's so weird. That means that the second link is up. Right. So, right, like I don't know why I just thought of this, but elbow down is like the gun show. And it's like that. This is elbow down, right? This is, I guess they're both the gun show, so it doesn't really matter. Anyway, so stupid. Theta 2 is positive for elbow down and negative. Right? So elbow up versus elbow down. So there's two configurations. Any position that we want to hit, right? You can have an elbow up or an elbow down position. Okay. The thing about these is that they should make a trapezoid when you put them together that share the same hypotenuse in the middle. So if you were to add this guy, put it over here, you get this parallelogram, right? Which everybody loves a good parallelogram, right? No, just me. That's fine. All right. So you can see it doesn't matter about the endpoint. We know where the endpoint is, but there are two possible configurations on how to get there. Okay. And that's what I was talking about at the beginning of class, right? So why would you test one versus the other? Well, I don't know what the workspace of this robot looks like, right? Is there something over here so that we can't go elbow up, right? We have to go elbow down, right? Is there something in the way that makes that not possible, right? And so those are considerations for a different class if you ever take ESG 330, which is Intro to Robotics, but you guys will all forget me talking about this by that time. Okay. All right. So again, probably going to be told whether you want to use the elbow up or the elbow down configuration when you're doing these problems, because it makes a difference, right? Makes a difference as to which angle you are going to be using where, right? Make sense? So let's just do one. All right, so I'm given L1 and theta 1, right? So this is weird. The way that we're going to step through this is we're going to do the forward problem first, and we're going to find P, okay? Then we're going to use that P, and we're going to solve the inverse problem to make sure we get back out the thetas that we started with. And then we're going to do the elbow down version of the problem, okay? So we're going to step through a couple of things. So this is the regular way, right? You're given the length and you're given an angle and you want to find the endpoint, right? That's where we're starting. So let's go ahead, right? I'm going to go ahead and draw my coordinates. X and Y. I used 45 degrees because it's very easy for me to draw 45 degrees. It's very strategic. All right. So L1 is at negative 45, which means that it's got to be here. Right. And L2 is at positive 45 to that angle. Right. So let me. Theta 1 and theta 2 is at 45 degrees to this. So it's gonna be like here. All right. Is that right? That's 90. Oh, wrong way. Sorry. So 90 would be straight up, and this is gonna be back this way, right? Back into the left, 45 degrees. Positive. I apologize. Remember, that's measured off of, well, no, I did that wrong again. Hold up. Please hold. Let me do it this way. This is 90 degrees. This will help. That's 45. Why? Because we're measuring off of this axis. So shouldn't that be touching the x-axis if they're the same length? Yeah, probably. Okay. So we want to find x and we want to find y. Let's start with finding x1. How do I find x1 here? Well, we just did it, right? This is my x1. This is y1. X1 is equal to 10 centimeters times the cosine of negative 45 degrees. So X1 is to be 7.07 centimeters. And because they're the same length and the same angle, right? Because it's the same length and 45 degrees, it's going to be 1 root 2 triangle, right? So X and the Y distances are the same. You can run the numbers, right, and do this for sine of 45, but cosine of 45 and sine of 45 are equal. It's 0.7071. And so multiply that by 10, 7.07 centimeters. Okay. That's X1 and Y1. Okay. Yeah. It should be negative. Thank you. Good catch. Should definitely be negative. My bad. Okay. So now what, right? So we've tilted this by 45 degrees, and then we came here and we drew this that was 90, and we're going to draw another line now at 45 degrees. This is not drawn completely to scale by any stretch of the imagination, right? But we're going to deal with it. Okay, so we're going to do the same thing now, right? X2. Well, in this case, X2 is going to be this distance, right? X2 and Y2. All right, so if you're looking at that, the angle that we need, right, if this is theta 1, right? You guys see what I've done there? I know it's crunched in there, right? So if you extend, theta 1 is going to, oh, sorry, theta 1's all the way back. No, theta 1's to the x-axis, right? Theta 1's to the x-axis. Does that make sense? You see what I'm doing? We're tracking. So what's the angle that we need for this triangle? If you're looking at this orange triangle, right? So let me draw it bigger. There it is, theta 2 minus theta 1. So we come up from this theta 1 line by theta 2. That brings us to our orange angle, right? But what we need really is this angle in here in order to solve the right triangle with sines and cosines. How do we get that angle? Well, we need to subtract theta 1. So theta 2 minus theta 1 gets us what we want, right? Well, theta 2 minus theta 1, isn't that just, is that 0? Yeah, man. Oh, man. How's that going to work? So I did not draw this to scale whatsoever, but this is going to tell me that this is going to be 10 times the sine of, no, sorry, cosine. 10 times the cosine of 0, right? Which is 1. Which is 1. And so this is just 10 centimeters. And y is 10 times the sine of 0 degrees, which is 0. So if we want P is going to be x1 plus x2, 17.07, and y is just negative 7.07. I didn't do us any favors by not using a protractor, but there's really no way for me to do that on the computer screen. I apologize. I'll figure it out for next time. So, do you guys have any questions? Yeah. So theta 2 minus theta 1. So it'd be 90, right? Is that 90? Is that correct? So it's, let's put it this way. Negative 45 is 315, right? Yeah. Yeah, 315 from there all the way around. So it'd be 315 plus that. Sorry. So let's think of it this way. Because it wouldn't make sense for this to be 90, right? Because then it's going to be right here, and that's right 90 degrees. So it'd be, you're telling me that would be here, and that's not correct. So let's try this. Let's think about this from a different perspective. All right. Here's my original coordinate axes, right? I have a line, this is at 45 degrees. Negative. I come over here, and this is 90 degrees, right? I'm just drawing a 90-degree line. Why would you do that? Because it's going to be helpful in a second. I'm going to actually do it in a different color. Do it in black. This is 90 degrees here, right? That would be my, I'm measuring now off of this, this link, right? So if we're doing this to scale as best we can. Right? So where's 45 degrees here? It's here, right? So by not drawing it to scale, I messed things up. If I have access to a protractor, I should use it to draw these because it's super helpful. Super helpful to draw these to scale. Is it reasonable that you would draw these to scale? Yes, 100%. Even if you're doing this in SolidWorks, you're going to have a scaled model of your robot arm, right? And then you can do dimensional analysis and things, right? From a mathematics point of view, we had to move 45 degrees and then we're coming back up another 45 degrees. It's going to cancel, right? Because it's not 45. So theta 2 and theta 1 aren't measured from the same axis to start with. And so that 45 degrees that we're measuring from theta 2 is actually 0 degrees. Okay. Is that a little bit less confusing? Maybe not. Yes. Draw it. So please draw it to scale if you can, or as best as you can. Okay. It's really helpful. And there's one problem in the homework, not this week, but next week, where you have to do a bunch of MATLAB, like use MATLAB as a calculator for a bunch of this stuff. And you're really going to want scaled drawings because there's there's 8 different configurations that it wants you to investigate. Which is, if that sounds super fun to you, you're right. All right. Okay. So we haven't talked about how to do the inverse of this yet, right? But we found the endpoint, right? And that's what we wanted to do. We found this endpoint 17.07 and negative 7.07, right? What about theta 1, right? If we wanted to find theta 1, well, we can use law of sines. Okay. So how's that going to work? Well, we have to define an angle that we're going to call alpha. It's going to be this small one in here, okay? And then we use law of sines to find alpha, right? Because we know this angle, and we know this angle, we know all the lengths. So we use law of sines to find alpha. Once we have alpha, then we draw the right triangle back over this, and we know that theta 1 has to be up to this link, right? So here's theta 1. So this angle in here is theta 1 plus alpha. And therefore, if we use the tangent, we can find out what the angle theta 1 is. Okay. So I, again, would probably call this its own angle, right? And just solve for what that angle is, and then, subtract alpha from it to get theta 1. Now, here's the thing. I know everybody's writing down these equations feverishly, and they will work. But you got to draw the triangles. You've got to, because sometimes in certain configurations, it's not going to be very clear where the endpoint is supposed to be with regard to what you're trying to do. Like, and so sometimes if it curls back very much on itself, right, you're going to have to really kind of try to figure out some of these intermediate angles using geometry. It's going to happen. All right. All right. Never mind. So here's the thing. Okay, it says theta 1 plus alpha for arm up and theta 1 minus alpha for arm down. Okay, it depends. It depends on where alpha is and where theta is. Okay, so please trust me when I ask you to draw it. I feel like I'm a broken record a little bit, but it's important. The drawing is important. The drawing. Okay. I promise. All right. Cool. Let's continue with this problem, right? So now we're going to take that same problem and we know the endpoint and we are going to run it in inverse and we're going to find the angles. So we know the answer is supposed to be, we're kind of cheating, right? But the reason we're doing that is so that we can prove to ourselves that this method works, right? That's the big idea. We're going to assume it for the opposite. We're now going to solve it for the opposite. So, all right. We're going to use the opposite angular orientation. So last time we had, what was that? We did elbow up last time, right? So we'll do elbow down this time. Let me double check what we did. Last time we did elbow down. We're going to do elbow up. There we go. Okay. So let's do this. We're going to draw. We're going to draw. And we're not going to get to the you got a problem today. So we'll get to it on Friday's class at the beginning. And then we'll get into vectors. That sounds like a great idea. Okay. So first thing we're going to do is if we're going to do this in elbow down, right? Sorry, elbow up. We have to mark P, right? And P, we know what that is, right? P, let's just remind ourselves, P is 17.07 negative 7.07. Okay, that's where P is. Here's P. Okay, great. Well, the first thing that we were told that we should do very many slides ago is we should figure out where the total distance is, right? We need that hypotenuse of this triangle. So we're going to find H, right? We know H because we know the X and the Y. So Pythagorean theorem, right? H is equal to the square root of X squared plus Y squared. If we plug those in and crunch that number, we will get 18.48 centimeters. So from the origin out to P, the straight line distance is 18.48 centimeters. Okay, great. Now that we have H, we know that these things have to be, and I'm just going to draw something, right? We're going to say that this is theta 1, and this is theta 2, right? And this might not be to scale, but I have something there that connects the origin to the other point, right? And we know L1 and L2 are both 10 centimeters, right? That's what we know. So what we need to do here is I'm going to find this angle beta on the inside of this, right? So how am I going to find beta? Law of cosines. Law of cosines tells me, is that an okay color? Not really. H squared is equal to L1 squared plus L2 squared minus 2 times L1 times L2 is the cosine of beta. So rearranging this, beta equal cosine inverse of H squared minus L1 squared minus L2 squared divided by 2 times L1 L2. This is negative, right? And there we are. So beta is going to be, well, we've got to crunch this, right? What's beta going to be? We've got H. So 18.48 squared minus L1, which is 10 squared, minus 10 squared divided by negative 2 times 10 times 10. And if we do this, what I got, and you guys tell me if I'm wrong, because you've seen it happen before. It's not a rare occurrence. It happens at least 3 times in class, especially with negative signs. So what do you guys get when you crunch this? Can you confirm or deny? Yeah. What we got? Yeah. Everybody, anybody crunch it? Or no? We just take my word for it. Yeah. I got some thumbs up. All right. Cool. Bless you. So beta is 180 minus, or theta 2 is 180 minus beta, right? Because beta is 180 minus theta 2. So move them over. And so we get 135. Now I want you to notice this. That's 45 degrees, right? 5 is just 90 plus 45. This is another 45-degree angle. So this is essentially 45 degrees off of that, but downward, right? Anyway, let's keep going. Should be pointed a little bit back, right? My point is I did not draw this well when I drew it, okay? But it should be extending back. All right, so we've got 135. Great, we need theta 1 now. So how are we gonna find theta 1? Well, remember, we need to define alpha, right? Alpha is this tiny angle in here. And now we're gonna use law of sines. So I'm gonna get rid of this guy here. We'll leave the result down there. So law of sines. Sine of alpha divided by L2 is equal to sine of beta divided by H. Alpha is equal to sine inverse of L2, which is 10, times the sine of 44.96 degrees divided by 18.48, which tells us that alpha is in fact 22.48 degrees. I don't know why I almost wrote centimeters. Okay. We're almost done. We're almost there. Because why? Because now we need to find theta 1, right? So look, this is the total angle here, right? That's the total angle. So if we want to find this tinier angle, we would have to take the alpha, right, plus theta 1 as our the tangent of alpha plus theta 1, right? Yeah. Tangent of alpha plus theta 1 is equal to x divided by, nope, y divided by x, like I said. Man, y over x. So we can say that theta 1 is equal to the tan inverse of y divided by x plus, no, sorry, minus alpha. And if we crunch that, we get what? Theta is a really small angle, basically 0 degrees. At least that's what I got. You guys, yeah. It's 0. Yeah. Which makes sense because remember what we had the last time. We had something at 45 and then something that was basically at 0. And if remember, elbow up and elbow down mirror each other, right? And so you still have the same endpoint, but it makes a parallelogram. So the angles should be almost inverted. All right. Next class, we will have you guys do, well, we'll check that. We'll do a MATLAB plot, right? And we'll do a problem. And then we will start. That's it. That's it for trig after next class. And we're into vectors, which is just this tricky way for me to get you to do more trig. So you guys know my office hours tomorrow are going to be shortened because of parent-teacher conferences. Yes, please. Yeah, put your protractors back in the basket, please. Thank you. Have a great rest of your day. Excuse me.